goodness. Okay. Good morning, good afternoon, everybody. Thank you for joining New Technology webinar number 5 with HEET. Really excited about the webinar today. I want to really welcome everybody to post the questions in the chat. Jesse, our co-host for today, is going to really read the questions up to our guest today. We're going to talk about decarbonizations, buildings, really exciting times for geothermal. So I'm going to just leave it with Sinead Magavi. And thank you so much for your time today as well and the presentations. Take it away.
Thank you so much. I'm really delighted to be here with you. And my name is Zainab Magavi. I'm co-executive director at HEET. We are a nonprofit climate solutions incubator based in Massachusetts. And we're a little unusual in our format. I mean, you got the nonprofit and incubator, that starts us off. We also take no funds from gas or geo or any related industry and attempt to build trust across the entire stakeholder network to drive systems change. And I'm going to start in a little unusual way as well on this talk about the birth of thermal utilities. I think it's an incredibly exciting talk. We're going to get a little more technical later, but first, what's the point? Well, for me, to be utterly honest, the point is my 3 kids, and they're actually teenagers. They won't let me show the older photos anymore, so you get this cute one. But we have to build a better world. Things aren't going exactly as we'd all planned a while ago. And so that's the big point, and it's good not to lose it. And what HEET does is tries to take on the entire system with the belief that if we solve one problem in isolation, we will not succeed. That instead it is an interconnected system with cascading challenges, and that what we have to really do is engage all the stakeholders across the whole system and build trust and innovate and iterate to solve the challenges in a kind of systems change way. And another way to say that is this: that in order to take on a system that is larger than you can really study or see in one go, you need many perspectives. It's a cute cartoon. The geekier way to say it is this little spider diagram I made of the different studies, the different research studies in Massachusetts on the thermal transition and what aspects they covered. And as you can see, each study takes a look very reasonably and rationally at a chunk of any given system. And understanding that and really trying to take on how they all interconnect rather than fighting over who's right or wrong is really the way we approach problems. And the first problem we approached in the gas system was that of methane leakage, methane being not just like one blanket carbon dioxide on the earth, but 84 times carbon dioxide in the first 20 years by sheer physical principles. It seemed like a great lever to pull in the climate system to reduce methane emissions. And so in order to do that, we got out in the street with the gas repair crews, really mapped all of the gas leaks and took on the challenge of using science showing that it's a heavy tail distribution in methane emissions, and developed a tool being demonstrated in the back there to find and repair the largest volume leaks, the super emitters in the gas distribution network, and brought together in this photo gas utility executives, climate activists, and everyone else in between, academics, regulators, and legislators, our now governor. And the beautiful thing was that there were no fistfights. And we use science as a common language to move forward with everybody. And that's what we keep attempting to do. And And so the challenge I'm here to talk about today with this lens of heat systems change approach is, the elephant in the room, the heating, the decarbonization of buildings. I guess I've got too many elephant cartoons, but let's see. So I think when you pause for a moment to really actually take in the scale of the challenge, and I don't think humans are that good at this, to be clear. If we need to decarbonize buildings in the coming century, it's 111 million buildings in the US, or 12,200 square miles of conditioned space, which is roughly the size of the state of Maryland. Even if we took on a third of that, that's 3,400 buildings a day for 27 years. So if you pause and let that sink in, the sheer logistical challenge, the monetary challenge, the human scale social challenge of that is enormous. And that's not the only system we have to decarbonize. So I just wanted to set that backdrop that we really have to be brave enough to look the scale of the problem in the eye. And the transition risks are very real. This is a photo from the Merrimack Valley gas disaster, where a pipe replacement through sheer human error unfortunately set 71 simultaneous house fires and took out the gas system for 8,000 homes. Safety, reliability, and affordability of the existing system, we've in some ways as a society taken for granted, and it can't be taken for granted. We must maintain safety, reliability, and affordability as we move forward in our transition. And I think that's critical to mention. And see, the other thing that's relevant to mention, and this is again an example from Massachusetts, is that many of our existing gas systems, and this is where I'm focused for the day with heating, since the majority of our home heating with fossil fuels is natural gas distribution networks. Many existing gas systems need major investments. So here in Boston area, we were very, very early. It was cutting edge in the 1800s. We still have pipe in the ground from the time of President Lincoln. It's very impressive. And it's leaking. And it needs major investment to reduce emissions and improve safety. But this is a map of all of the pipe replacements scheduled for the next 5 years. And that's a lot of work. That's a lot of opening up our streets and orange cones. And it's projected to add up to $40 billion. And that's money spent not to decarbonize, even at the same time that we're going to decarbonize. And so that is also a challenge. So I've been laying out challenges. I'm going to keep going for another minute or two, and then I promise we'll get to solutions. And the part where it is not individual buildings, but a network of buildings interconnected by the natural gas network brings up another issue. If you take the approach currently proposed by most states, a building by building electrification of individual buildings, what happens is one by one, you're taking them off of a network with a fixed cost. And what that does is it raises the cost for those remaining on the network. If you keep going this way and you end up with one last building, the Germans actually call this the last grandma problem, that there's some grandma holding the bill for the entire network. It's not unrealistic. This is a real challenge, and it triggers what's known as a death spiral for a utility. We don't want to go there because it has kind of cascading challenges. So just to summarize our extensive stakeholder outreach and definition of the challenge, this is what we discovered, that the needs that would meet all of the stakeholder requirements. So the gas workers want to keep their good jobs. The utilities need a system, a business model transition that makes economic sense, that keeps safety, reliability, affordability. We need to do this equitably with security. And we need to cut the emissions. We also need resiliency, efficiency, scalability, and adaptability as our world changes. And then finally, that back to the scale, we need to go at the speed and the scale needed. Now, when we first put this out there, probably in 2016 or 2017, Yeah, people looked at us like we had two heads, like, okay, good luck. So we kept trying to find a way to do this. And I want to shift for a moment to geothermal. And just acknowledge quickly before we dive in that the word geothermal is used for many technologies. One could think of it even as geothermal is the last name, and each family member is an independent individual. So we are not talking about geopower. We're not talking about district geo, where you use direct use hot water to pump it around in a system to provide hot water to buildings. We're not talking about individual geothermal, which is in the shallow borehole, say 100 to 1,000 feet, and ambient temperature, doing heating and cooling across the year. What we are talking about is something a little newer than that. Networked geothermal, networking ground source heat pumps, which basically creates something that has about 100 names, and we're going to just assume that a rose by any other name would smell the same. It's been called the Geomicrodistrict, the Geogrid Thermal Energy Network, now in New York, 5G HCD in Europe, the 5th generation, TENS, GeoNet, HEETnet. The jury is out on what it's going to be called, but what it is clear. It's every building, every customer building has a heat pump, ground source heat pump / water source heat pump, which pulls heating or cooling as needed, perhaps an array of heat pumps, off of a supply and return pipe, a service loop from the thermal utility. And the service loop comes off a main loop in the street, large pipe filled with water. In some cases, people choose to add glycol. There are systems with both options, but the water carries the thermal energy and is the loop in the street, the main loop that has service loops off of it. That temperature is maintained by shallow, quote unquote, closed loop vertical boreholes, either in the right of way or as accessible in parking lots, sidewalks, etc., as well as any other thermal sources or sinks. So just to highlight a couple of the key pieces of this design, there are many ways to network a ground source heat pump. And just like the difference between an individual computer and what happens when you network computers and get the internet, you get emergent properties. And what is specific to what we proposed in the gas to geo transition is you want to stick with the ambient temperature single pipe or ambient temperature loop, which allows bidirectional thermal flow and waste thermal recapture and heating and cooling flexibility to meet changing loads. It also allows flexibility of interconnection and a growth model. You're going to calculate the load stochastically rather than the straight sum of the loads, and therefore reduce infrastructure costs. And you're going to use opportunistic design. Really think big in terms of thermal. There's a lot of thermal out there, and use whatever local thermal opportunities you have, perhaps thinking of the geothermal bore field as your base load, and other thermal opportunities as on top of that. So just to slow down there a bit and dive into this. So here we have an ambient temperature loop and a bunch of buildings. Here's an example. We've got, maybe it's a supermarket, maybe it's an ice rink, but it's cooling and rejecting heat or dumping heat into the ambient loop. I've pictured it as purple, both red and blue. And these other buildings are in heating mode and they're pulling that heat off. In this situation, you have an energy sharing that is like a new kind of energy efficiency that emerges when you do this interconnection, that would not be there with individual geothermal installs. And so this is allowing a synchronous load cancellation. If you have simultaneous heating and cooling in your district, which is almost nearly, it's often present, particularly in mixed use settings, you have this instantaneous load cancellation through the ambient loop. And if you add the boreholes, and you will, you have another phenomenon whereby there is a ability to load cancel asynchronously. So perhaps the most extreme version of this is, here we are in the middle of the winter, everybody's heating and we're dumping heat into the ground. And then, oh, yeah, my slide didn't work. Right, one moment. And then we shift to, it gets suddenly hotter outside, and we my slide didn't work. I will just pause for a second. So the most extreme example is dumping heat into the system in the summer and pulling it out as it gets colder to heat. And that has been documented in some systems. We've often in geothermal called it thermal drift, and done everything to design around and avoid it. However, it is something we could actually tap into and use more directly and intentionally as thermal energy storage. There really isn't a difference between thermal drift in geothermal and thermal energy storage. And it happens naturally in individual systems, just on a short turnaround. There is a thermal capacity even in the loop and in the ground that allows any peak to be spread out, and that asynchronous load cancellation happens at many time scales, less over a long time scale. All right. So one of the things that we did after proposing this gas to network geothermal transition in 2017 was, after long conversations with our gas utility executives, we got together a list of the questions they needed answered. And we hired Bureau Happold Engineering to do a statewide feasibility study, technical and economic, to attempt to do the first effort to address what would happen. Gas system segment by segment, if we replaced it with ground source heat pumps networked with boreholes in the right of way. And one of the things that emerged was the opportunity in that annual load balancing. And as you can see, the greatest opportunity for a balanced system is in those high density mixed use sites or street segments. We modeled the Massachusetts gas network into representative street segments. And that's actually really exciting, because it means you're going to get your greatest energy efficiency in those high density mixed use settings that are actually the most challenging to decarbonize. So that's a nice, sweet intersection. And part of what's happening that I want to make sure to comment on is that when we're interconnecting them and managing by a utility, the risk of thermal drift is addressed by thermal management at the central utility, and the opportunity to use all of the thermal capacity available at a site can shift. So here on the left is a non-interconnected street segment, and because we can't shift over 100% on the heating, we do not meet all of our cooling needs. When you shift to this right chart, what we're doing is actually drawing the heating out and sharing it with another street, shifting it to a street that needs more heating and less cooling. And then we are able to actually get more energy out of that existing identical infrastructure than we would otherwise get. So there is this lovely economy of scale when you begin to interconnect across a large system. Doing something a little bit like this, our first proposed individual street segment, geo microdistrict, in replacing one segment on an outer branch of the gas system, and then incrementally interconnecting them. And they proposed and expected outcome is to have an increasing efficiency as you increase the diversity of load and the number of customers. And on an individual basis, our feasibility study found that even without that interconnection, and using only the right of way and a limit at 500 feet and spacing every 20 feet, you could still meet 100% of heating and cooling in more than half of the existing street segments in our Massachusetts gas system. We're a heating climate. And so when you start to look at replacing or electrifying, really zonally electrifying by street segment. You have a huge opportunity to avoid the death spiral that individual building electrification will trigger in the gas system. Customers can stay with the utility, go from being a gas to a geo customer. Energy bills can stay low. You can merge the rate base, and the geo customers can carry the gas customers out until the gas system is right-sized to, for example, necessary industrial use. A projection by Massachusetts gas utilities will show you here the building by building transition off gas for energy burden for low-income customers versus the gas to geo transition as the minimal energy burden for low income. And other projections by the Applied Economics Clinic show, again, that the cost today and going forward for a monthly bill for this network geosystem could be, if rate makers use the same techniques as they do today for gas, it could be lower than gas. And of course, there are dramatic emissions reductions immediately, over 60%, depending on your electric grid, of course. And you can get to zero if your electric grid can get to zero. And one of the sweet, lovely intersections is that the pipes on the top are gas pipes, the pipes on the bottom are water pipes. The only difference is the stripe. And so we have a large number of gas workers and unions that have key transferable skills. It's really nearly the same job with a little less safety risk. And that is part of why we have national support, apologies, from the UA for electrification via thermal networks, and many other relevant unions are backing this and proposing it across the country together with gas utilities and environmentalists. We're actually calling that combination the triumvirate. And I want to pause for a second from that's the social change driving, but there's another large scale technical effect on the system. And that is that higher efficiency technology can minimize electric grid impacts and costs. This is a model, and sorry for the whiting out at the top, I'm trying to simplify it, but commercial, industrial, and residential electric building energy use for the US. And this is a projection. If you took all of the fossil fuel used today in buildings and magic wand waved it to electricity using different technology efficiencies. And what you can see here, we're calling this the Falcon curve because it's a lot scarier than a duck curve, is that if we did that by electric baseboard, which no one is planning to do, we would have to build out many, many times the electric grid just for the building transition alone. And we would create a giant peak in the winter, which would also raise our prices for electricity, given the gap between the trough and the peak on that curve, or the load factor. And so what it shows is that the more efficient the technology we deploy for building electrification, the less impact on the electric grid in terms of cost, and the more feasible it is to get to our decarbonization goals. One of our case studies has recently published a coefficient of performance that ranges between 5.7 in the summer to 8.9 in the winter peak, which is astounding. It's much higher than I have modeled in this publication. So there are, here's a little bit of a window into that installation out at Colorado Mesa University. It's been in the ground for 15 years. And this is their monthly electric load reported from Xcel Energy as it moved from 800,000 square feet to 1,200,000 square feet. You can see how it's extraordinarily corralled. And Xcel Energy was so curious about this that they are now moving forward with building network geothermal. And this is the university that this data came from, and some quick pictures of the real infrastructure that's been in the ground. They've got a 12-inch main loop. They've interconnected 5 loops over time, grown the system. Here's a pump station at the bottom. And the thing on the right is a rather beautiful heat exchanger with their irrigation system, which they use as a novel source and sink to dump heat in the evening onto the lawns when their summer cooling system is up, and they save an enormous amount of energy by doing this. This is just a quick diagram. Their initial total system cost of 8.2 million, and they have covered 100% of their heating demand and cut their water use by 60% through the reduction of chiller use, which, given that they're on the Colorado River, may be one of their highest impacts. To give you a sense of the scale of this, they've got 427 boreholes, which actually is proportionally much less than you would ever estimate as a rule of thumb in an individual system for that load. And they are currently, thanks to the Colorado governor's wonderful support, expanding to cover the entire campus and doubling the size. And there's a bunch of us that will be studying that process. I'm going to skip this part and mention that we at HEET think that one of the most important things to do now is to study the systems going in the ground as rigorously and thoroughly as possible in order to best define this industry going forward and set standards that give us the best outcomes and get us all of those diverse stakeholder needs. So we've launched the Leg Up research project, Learning from the Ground Up, thanks to the exciting news that Eversource Gas and National Grid Gas here in Massachusetts are fully permissioned and currently installing network geothermal in communities here. In fact, I am actually sitting in Framingham right now, where 80% of the street loop for a 1.5-mile loop in Framingham is already in the street, and they've got 2 different bore fields in drilling process. One of them actually has a directional drill that is a direct import from the oil and gas industry, thanks to Schlumberger's spinoff, Celsius. And that is it's a perfect example of the intersection and the need in this industry to tap into the knowledge and expertise of the oil and gas industry. So our research team is working together with Eversource Gas, National Grid Gas, and the folks doing the installation to fully evaluate the potential of network geothermal to deliver heating and cooling in Massachusetts and help prepare communities to adapt. In order to do this, we are studying every bit of data we can get off the gas to geo installations, as well as putting, for example, fiber optic cable into a set of boreholes to have continuous thermal monitoring of the entire ground formation over the coming years. We are building models, and I'm just going to break this out. We're going to build 4 models based on the installs using the real data for this technology and its behavior, and then use those models to project impacts of fully scaled installations on things like the electric grid, costs, health impacts, equity, environmental, and we're also creating community feasibility studies to be ready for that scaling. So the core modeling is in process right now. We have both a full physics and reduced order model, and again, are really tapping into a lot of the expertise of the oil and gas industry. Here's a quick image of some of the approaches. That's for a Modelica model. And then we've got all of the externalities. We're trying to quantify and model them and put them into our equation. This is part of our view of systems change. And then finally, the statewide assessment is really to enable decision makers to make wise decisions and to quantify and increase safety, et cetera. We're really excited that the federal government has gotten involved, launched the first ever community geothermal FOA, and there are 11 projects moving forward across the country. There's one in Oklahoma, there's 2 in Alaska. We have an additional one in Massachusetts to demonstrate expansion. And this is a picture with the geothermal industry with Secretary Granholm, who has just declared so much support for all of the geothermal family. And of course, we are, as everyone seems to be, greatly positively affected by the Inflation Reduction Act. This is the time to grow this big. And coming back to that question of scale, this is an image of our gas system. And it is actually quite beautiful. I mentioned that, it was cutting edge, and the time of President Lincoln. We have a pipe right in the heart of Boston that is from the 1860s. And we really have paused and thought about the people that put in those first pipes and imagined this system before it existed. And I think what we have to realize is today, we might see our world as being a series of great challenges, but in great challenge, there is great opportunity. And we have the once in many lifetimes opportunity of reimagining our energy system and beginning to meet the needs of future generations and the different challenges of today. So what we know we have to decarbonize buildings is we have individual air source and ground source heat pumps, and we have RNG and hydrogen for combustion dependent buildings. What we strongly believe and have plenty of evidence to support is that the remainder of our gas system that doesn't happen to go for one or the other of these is absolutely able to meet decarbonization in a way that optimizes for safety, emissions, cost, reliability, and equity through the gradual gas to geo transition and the growth of these thermal networks. And one of the things that I want to make sure to say is that if you build a thermal network, you have built a thermal market. And that thermal market is part of the energy system of the future. And it was a lot of information I just threw at you. So I just want to pause and get really simple for a second. When you look at this cup of coffee, and that's what I try to do every morning, is look at a cup of coffee, you can't tell, and I can't tell if that is hot or cold. And the very simple truth that thermal energy is not visible has, I believe, led to us making a critical error in our energy system planning, and ignoring what we do not see easily. And let's see, there we go. When you get a thermal camera and start looking at the world in a different way, it's pretty fascinating. Here's a couple pictures with a thermal camera. I'm sure you can figure out that that's a road on the left and some bats on the right. But it is pretty fascinating how much waste thermal there is all around us. And once you have built a thermal network with the ground source heat pump and geothermal borehole, with the geothermal borehole as a form of baseload of insurance and ability to store energy, bringing onto it all of the available thermal sources and sinks in our environment is going to dramatically increase the efficiency even over what we have already calculated. And just to give you a quick example of some of the fun we can have when we start to see thermal, this on the left is a picture of the Olympic Media Center in China. And one of our friends did the design for this. There is underneath the dock on the right, there is a titanium seawater heat pump, and it is pulling temperature off of the bay to heat and cool that media center. Have you ever looked at here in Boston, we have a bay that is warming and the lobsters are leaving. Looking at that problem and seeing instead that we can pull heat off of our bay, make the lobsters happy, which makes all of us happy, and then provide a certain amount of heat to our downtown district. That's the kind of thinking we need in this new energy future. And I'm going to leave us with a really, really big picture, zooming way back out. I'm sure you've all seen these Sankey diagrams. What I want to point out is that 65% of the energy that we consume is over here on the right, rejected. And a huge percentage of that is thermal waste. So there's an opportunity even beyond the potential of the gas to geo transition, which is to build this thermal market and tap into our waste thermal as well. So I hope you're excited about the crazy potential of a gas to geo transition, and I look forward to your questions.
Thank you so much for the presentation, Sanip. I'm gonna get the questions going with the first one. I think the IRA is obviously bringing significant incentives to the industry to look at different type of energies, and geothermal has been getting a big push with the current administration in the US. The question is, how much do you think off-takers or actually building owners are really aware of the potential financial benefits that comes with thermal energy implementation? Anything you can share in that direction, Sanip? Thank you.
Yeah, I think they are very minimally aware. And it's a huge challenge that I know the federal government is really trying hard to figure out how to do the kind of nearly grassroots outreach necessary to get it going. I think once a certain critical mass of people have tapped into the cost savings, it'll go word of mouth, and more and more people will be more and more aware. But right now, at this very beginning, even those who are aware are a little uncertain of timing and process. A bunch of the rules recently came out around what qualifies for different aspects of the tax rebates, et cetera. And I think we're in that uncertain space where people are excited. There's a bunch of industries that are moving to prepare and moving to scale, but I think individual building owners are not yet fully aware.
Thank you, Sanip. The next question is, at 500 feet, there is usually fresh water in the system. So how is the system isolated in terms of assurance for the life of the cycle, the life of the process?
So to be clear, you could design any kind of borehole, including an open well. We have only proposed for this gas to geo transition the closed loop vertical borehole. And it is drilled in a typical water well way, currently about a 6-inch wide hole, again, 100 to 600 feet typically. And then a U-bend HDPE plastic tube is inserted into the hole, and the remainder of the hole is filled with a thermally conductive grout. So the actual thermal transfer happens in the water that travels in the U-bend down the hole and back. It does not have direct contact with the groundwater. Of course, groundwater presence increases thermal conductivity in many cases. You know, when you're drilling, you can sometimes hit a seam of higher flow water, which is currently dealt with by sealing it off, so that you don't have any environmental challenges of moving between layers and contaminating. So I think there's so much potential, and I'm like aware of the group here. There's so much potential to shift learning from oil and gas drilling and improve the efficiency and the process and all of the potential of these boreholes. And Celsius, who's very nearby to me right now, drilling for the Framingham Eversource gas project. I was meeting with one of their drillers this morning, and they are really actively bringing a lot of the technology. They've instrumented the directional rig with a whole lot of sensors to really locate in 3D their bit as they drill, which is not typically done in water well drilling. And that's very exciting to the utility, who wants a lot of replicability and safety in the process. That was kind of a long answer, but.
Thank you, Sanip. Next question. In your opinion, do you think the geothermal network distribution should be public or private, meaning owned by the government or by the private sector?
Yeah. I appreciate you asking in my opinion. This is a hot topic. There's a lot of debate. There's a lot of people who are like, oh, well, we should utterly privatize and this it'll go fastest if they're third-party owners, et cetera. I think the technology should happen no matter what. However, given the following, that the existing gas utilities really do have need of a business model going forward in order to stabilize the rate base, not have spiking prices, to transition their workforce. And given that they already have the rights of way in the street or grants of location, they have the customer base, the billing, the ability to do in-street construction, and they can most safely transition their own system. I am firmly of the opinion that we should have the gas utilities, whether they are publicly or privately owned, be the drivers of this transition whenever possible. Where it ends in the end, and who owns it in the end, if it becomes municipal, that seems to work quite well in some of the European countries. I do not have as strong an opinion. I'm more focused on the decades of transition that we face in front of us.
Thank you so much. Another question, Sunny, when we talk about geothermal power generation or any power generation projects in general, commercial models are around power purchase agreement. With the heat or heating and cooling from your value proposition was typically the commercial model with building owners.
Yeah, I don't really have I don't feel that I know enough about power purchase agreements to understand the potential or weigh in on that.
Perfect. Next question. Do the homes need to have any sort of electrical power equipment or systems that can work with the system that you propose?
Yeah, so I probably should have shown photos of what's happening right now here in Massachusetts. The project here in Framingham is not replacing the gas system. It's testing the heating and cooling potential of the network geothermal. And so they are doing the following to their participating buildings. They're doing weatherization and air sealing weatherization, and then they are also doing a replacement of the HVAC system. So replacing a gas boiler or an oil boiler or electric baseboard with a ground source heat pump. In the best way to answer building transition is every single building is different, but just generally, if you have a steam distribution system, you're going to be replacing it, though there are prototype heat pumps that can hit those temperatures. It's not on the market. And if you have no ductwork, but have hot water distribution, you may be able to adapt it, but you won't be able to get air conditioning. So there's the need for a lot of different approaches to different homes with different HVAC ages and systems. So the second project going in the ground is in Lowell, Mass, and that's with National Grid Gas. And they got permission from our utility commission to go ahead and actually fully electrify the customers. So at that point, you then have to transition whatever other gas appliances you have, whether that's a stove, a fireplace, a hot water heater, dryer. And I just want to mention that a ground source heat pump can provide direct use hot water, indirect use, and direct use hot water. So they are actually replacing all the appliances. The challenge of who's going to, in non-demonstration projects, actually cover the costs of that is a real one. I really don't think we're going to manage to do a building decarbonization transition if we ask everybody to pay for it. I don't think there's any chance of it. And so I do think that the utility model, where we pay for upfront infrastructure with long-term incremental payback, is a really brilliant model that really was what allowed us to grow the amazing energy system we have. And I think we need to deploy that model again and use the utility model to do the full building transitions in the coming decades.
Thank you so much. One more question that is really interesting. I'm going to read it completely. The technology, the option for the geothermal network technology has so much potential. Are there any benefits to pairing thermal energy with storage in buildings in order to really have a backup for the up and down peaks?
Yeah, so you're asking about any benefits to thermal storage on an individual building basis.
Absolutely, and especially in the winter, which is the bigger concern with electrification.
Oh, it's going to be so fun when people catch on to this thermal networks potential. Yes, you could put all kinds of different thermal storage on a individual building scale, and or on a once you've built enough of once you have enough customers on a network, suddenly the scale of thermal storage you see in some of the European like ATES and BTES, borehole thermal energy storage, larger scale, hotter or colder thermal storage, ice storage even, starts to make economic sense when you have the scaling. But on the building scale, absolutely. This is the beauty of a both distributed and centralized system with bidirectional management. And you could, for example, put solar thermal, which is an incredibly efficient form of capturing solar energy. Solar thermal works. You could put a giant molten salt battery and shift thermal. You could take the excess wind energy in the middle of the night when no one wants it, store it as thermal energy, and use it in the thermal network to provide heat.
Thank you, Sandeep. Another question: who will make the decision, or who is actually the leading entity, person, organization that decide how much heat will be allocated and distributed across the entire system or building?
So there's a lot of decision makers in the system, the way I see it. And first, I want to be clear that the individual building owner, customer, renter, whatever, the customer does control their thermostat and makes the decision how much thermal energy, whether heating or the absence of cooling, they are moving into or out of their home. And they will pay for the electric cost of the heat pump. But the question of how much, how to maintain the thermal supply for those variable customer demands will be, in my mind, a utility question, regardless of the ownership model of the utility. So that is part of why we're building these models with Lawrence Berkeley Labs and NREL and others, is to have really data-based ways to predict the loads and demands over time and space. One of the beautiful things, however, about a geothermal network is that, unlike on the electric grid where you have a fraction of a second peak, more similar to the gas grid where you are able to change pressure and therefore can spread any peak to a couple hours. This thermal system really can spread peaks even longer. I'm calling it thermal packing instead of line packing in the gas system. So the ability to spread that peak and the resilience of the system with thermal drift that really needs to be managed on an annual basis allows us to have a learning curve where we can do our best prediction, we can do our best models, and then really get real-time data and adjust as we go. One of the beautiful things on a central loop is you can have a backup thermal source and sink. You can have a boiler and a chiller that can allow you to shift the temperature of the loop if you really are straying out of the range that you're aiming for. And of course, there's a paradigm shift under this, which is the aim of the management of a thermal system is to maintain it in balance over time at different time scales. And so you want to keep the temperature as close to the ambient temperature of the ground and basically pull a balanced amount of heating and cooling over time. Very different from the design of a peak load system. So you can ensure your peak load with backup systems on the loop. Again, I think it's the utility that needs to do that design. I don't think that it's in a category of something like FERC because you don't have interstate connections necessary because it's a more locally without interstate transmission lines required more local decision making. So a regulated utility, regardless of ownership models. That was a long answer to a short question.
Thank you so much. One more questions before we close the session. With the geothermal loops, what's the level of corrosion and what's kind of the corrosion management program? Is there any sort of additives specific that you can talk about to manage the corrosion? If so.
Oh, corrosion, yeah.
Yeah.
It's minimal. The O&M costs for these systems are much lower than existing gas distribution networks. And they're typically currently using HDPE plastic, and the expected lifespan is well over 60 years, likely 100 with there is some need for management of the water quality for mineral buildup. And some systems use some water additives. I am not an expert in that technology, but I do know that the O&M costs and lifespan are significantly longer than any existing system. Sorry, the O&M costs are significantly lower and the lifespan is significantly longer.
Perfect. And I think with that question, we can close the session. We thank you so much for the presentation. Thank you, everybody, for joining GTTS New Technology Webinars. We look forward to seeing everybody in the next session. Have a great remainder of the week. Great weekend. Thank you so much.
Thank you all, and good luck.
Thank you. Bye.